5.5 years ago, in the pre-dawn hours of September 25th, 2019, the first commercial flight lifted off from a brand new runway in southern Beijing. The cameras caught it, the dignitaries clapped, and in a quiet monitoring office, a small team of geophysicists was already looking at numbers nobody on stage would have wanted to see. The ground beneath parts of the runway was sinking, not in inches per decade, in inches per year. Beijing Daxing International Airport, the mega project that swallowed an entire $120 billion economic zone south of the capital, had opened on terrain that geologists had been warning about for more than a generation. Satellite radar surveys peer-reviewed in journals including the Journal of Sensors and the science publisher Elsevier had detected ground deformation reaching 70 millimeters a year in specific zones. That's roughly 3 inches every 12 months. And the surveys are still showing movement today, which raises a question the Civil Aviation Administration of China has not answered publicly. What happens by 2028 when those millimeters add up? To understand why this airport is moving, you have to understand why Beijing built it here in the first place. By the late 2000s, Beijing Capital International Airport was choking. It was already the second busiest airport on Earth. It had absorbed an Olympics. And by 2018, it was handling roughly 100 million passengers a year on infrastructure designed for 83 million. Something had to give. The Civil Aviation Administration approved a second international airport in December 2014. The chosen site sat 46 kilometers south of Tiananmen Square in Daxing District. The location made political sense. It would anchor the new Beijing-Tianjin-Hebei integration zone. It would push development southward. It would be reachable by high-speed rail in 20 minutes. What it would not be, what it could never be, was geologically simple. Daxing sits on the alluvial plain of the Yongding River. The ground here is layered, fine-grained sediment laid down over thousands of years. Underneath all of it sit confined aquifers that have been steadily emptied since the 1970s by a thirsty megacity above. By the time the airport's foundation was being poured, the southern part of Daxing had already cumulatively sunk more than 900 millimeters since 1995. That's a meter of vertical drop before the first plane ever landed. The first hard data on what was happening came from satellites, not engineers on the ground. Researchers using Sentinel-1A radar from the European Space Agency tracked the airport's surface deformation between July 2017 and June 2019, the construction phase. The findings were published in 2024, after years of follow-up monitoring. The results were not catastrophic, but they were not boring either. The cargo apron was the worst affected. Maximum subsidence velocity reached negative 70 millimeters per year in localized zones. Cumulative settlement on the cargo and maintenance areas reached 115 millimeters and 80 millimeters, respectively, before the airport even opened. Now read that again. Before the airport opened, parts of it had already settled by the height of a Coke bottle. A second study, this one fusing Sentinel-1 data with Germany's higher-resolution TerraSAR-X imagery from January 2021 to October 2024, refined the picture. Across the operational airport, deformation rates ranged from negative 70.3 millimeters per year in the worst zones to positive 20.4 millimeters per year in others. The whole site is breathing, some sections sinking, some rising slightly, none of it uniform. That non-uniformity is the part that keeps engineers awake at night. Here's something most people get wrong about subsidence. A runway sinking evenly at 3 inches per year is an inconvenience. You can grade it back, you can repave. You can absorb it in the maintenance budget. Airports do this all the time. It's not glamorous, but it's manageable. A runway sinking at 3 inches per year on one end and rising at half an inch per year on the other end. That is a structural problem. The damage isn't from depth, it's from gradient. When two adjacent zones move at different rates, concrete pavement experiences shear stress it was never designed to handle. Cracks open, joints fail. The smoothness tolerance for an aircraft runway is measured in millimeters across hundreds of meters. A jet touching down at 250 kilometers per hour cannot encounter sudden surface elevation changes of even a few centimeters without consequences, ranging from violent vibration to costly gear stress. This is exactly the pattern researchers identified at Daxing: seasonal acceleration during summer rainfall and high temperatures, construction-driven subsidence funnels in specific zones, thermal expansion in the terminal building creating periodic deformation that rides on top of the long-term sinking trend. It's not one problem, it's 3 problems happening on the same patch of concrete. And by 2028, assuming current trends hold, some of those zones will have accumulated enough differential displacement that existing pavement tolerances will be tested. To see what could happen at Daxing, you only have to drive 65 kilometers north. Beijing Capital International Airport, known to aviation by the code PEK, has been operating since 1958. It sits in a part of northeastern Beijing that the geological literature describes as fine-grained sediment overlying severely depleted aquifers. Maximum subsidence rates in the surrounding districts exceeded 100 millimeters per year in past decades. The airport itself has been sinking for years. A 2020 study using Italian Cosmo SkyMed satellite imagery measured a maximum subsidence rate at PEK of 50 millimeters per year. More importantly, the researchers identified linear subsidence boundaries that lined up exactly with mapped geological faults. One of those boundaries runs near the middle section of Runway 2. The differential there exceeded 30 millimeters per year between adjacent zones. In follow-up research using Sentinel data from 2015 to 2021, the analysis flagged something more pointed. Most major roads and runways in Beijing remained stable. But PEK's middle runway, the researchers noted, showed abnormal deformation gradients, specifically called out as indicating potential structural risk. Capital Airport has a head start of 61 years on Daxing. It is already showing the symptoms researchers worry will eventually appear at the newer megaproject. And it is doing so in spite of every engineering control China has thrown at the problem. You cannot understand any of this without talking about water. Beijing has been pulling water out of the ground faster than nature could replace it for more than 5 decades. According to the Chinese Academy of Geological Sciences, the city extracted more than 600 million cubic meters of groundwater above sustainable levels every year through the 1980s and beyond. Until recent reforms, somewhere between 70 and 80% of Beijing's water supply still came from underground. When you remove water from a confined aquifer, the clay and silt layers above it, what hydrogeologists call aquitards, slowly compact. The grain matrix collapses, the land surface drops. And here's the cruel part. The compaction is largely irreversible. Even if you put water back in the squeezed-out aquifer space, does not fully recover. That's exactly what's happened across the North China Plain. Cumulative subsidence has exceeded 3 meters in some sections. The plain has been sinking since 1935. The Beijing Plain alone has 5 major subsidence funnels with maximum recorded rates of 137 millimeters per year in Haidian and Chaoyang districts during peak depletion periods. Daxing is one of those 5 funnels. The airport sits inside it. The aquifer compaction is driving the surface deformation researchers see in the INSAR data. And the geology gives no indication of stopping on a useful schedule. So why pick 2028? Because that's roughly when several of the trend lines converge into a problem that becomes harder to fix than to anticipate. If you take the current peak subsidence rate of 70 millimeters per year and project forward from the latest published data, October 2024, fused Sentinel and TerraSAR X, you get an additional cumulative drop of roughly 210 to 280 millimeters in the worst zones over the next 4 years. That puts portions of the cargo apron and adjacent surfaces near the upper edge of what international civil aviation pavement standards consider acceptable for differential settlement before significant structural intervention is required. It also matches the operational milestone Daxing was supposed to be hitting. By 2025, the airport was targeted to be processing 72 million passengers per year. By 2028, the second phase of expansion was scheduled to come online. More terminals, more runway capacity, more load on a foundation system that was already not behaving as designed. The 2028 cracking scenario is not a prediction, it's a threshold. It's the date by which, if the deformation rates published in peer-reviewed monitoring don't slow down significantly, parts of the runway system will need substantive repair to remain in tolerance. Here is the part of the story that does not get enough airtime. China is not ignoring this. Since around 2016, satellite monitoring shows Beijing's wider land subsidence trajectory has been bending. The maximum rates are not what they were in 2010. The most aggressive subsidence funnels around the city have decelerated. In some specific zones, Xunyi, Huairu, Pinggu, the surface has actually started to rise. The reason is the South to North Water Diversion Project. Approved in 2002 and operational on its central route since December 2014, the project pipes water from the Yangtze River Basin more than 1,000 kilometers north into Beijing. Since opening, Beijing has reduced its dependence on groundwater. The city has imposed strict extraction limits since March 2014. And in places where artificial recharge has been deployed, like sections of the Caobai plainland that was sinking, has reversed and is now rising. But the recovery is uneven. The hydrogeologists who published the tri-decadal Beijing plain analysis in 2023 were clear about one thing: the most severely sunken lands and the most heavily compacted aquitards will not recover. The damage is, in their term, irrecoverable. Subsidence at Daxing has slowed since 2016, but slowing is not stopping. And stopping is what would be needed to fully eliminate the 2028 cracking risk. This is where the engineering community splits. One camp, including several authors of the 2024 Sentinel TerraSAR fusion study, argues that the absolute deformation rates at Daxing are still well within manageable limits, that the concrete pavement is already designed for non-trivial differential settlement, and that the airport's continuous monitoring program will catch dangerous gradients in time to schedule maintenance windows. In their reading, this is a story about successful engineering vigilance, not impending failure. The other camp focuses on what the data does not show. INSAR has known limitations, decorrelation in vegetated areas, gaps in coverage. The difficulty of calibrating absolute elevations versus relative motion. They argue that the published rates likely underestimate the worst pockets, that summer acceleration patterns are getting more pronounced, and that the runway middle section anomaly, already detected at Capital Airport, is a preview of what will eventually emerge at Daxing. Both readings are defensible from the same data set. That's the uncomfortable part. The honest answer is that nobody outside the Civil Aviation Administration of China currently has the proprietary high-resolution data needed to settle the argument. What is certain is this: Beijing Daxing is the world's largest single-structure airport terminal. It serves more than 100,000 passengers a day. It anchors a regional economy now valued in the hundreds of billions, and it is built on ground that has been moving for 90 years and has not yet stopped. Between now and 2028, three things will determine whether the cracking scenario actually arrives: whether the south-to-north water diversion can sustain its groundwater offset, whether the deformation gradient at the cargo apron stays inside acceptable pavement tolerances, and whether China's Civil Aviation Authority publishes, or quietly absorbs, the maintenance bill the Earth is already drafting. What the satellite record makes clear is that infrastructure does not negotiate with hydrogeology. You can pour the strongest concrete on the planet. You can engineer the cleverest foundation. You can pump in geothermal heating and cover the roof in solar cells. None of it changes the fact that the aquifer 50 meters below your runway is still adjusting. In 2028, we will know which side of this argument was right. Until then, the satellites keep watching, and so should the rest of us.